Let's now talk about how we can use the GPT model to generate actual text. So in the previous section, we implemented this GPT model architecture, and we have seen that it outputs this tensor. So it doesn't look like text at all yet. So there's something else we have to do now. So one thing I mentioned before is that if we have 4 input tokens, we get a tensor here consisting of 4 rows, but each row is 50,257 dimensional. So how do we get these 50,257 dimensions back into words? That's the focus of this section. And so one thing before we get there, I wanted to mention is LLMs generate one word at a time. So if we have an input, hello, I am, it might generate the next word A, and then we concatenate the A back to the input, hello, I'm A, and then in the next round, it generates the next word and so forth. So it's actually an iterative process where we are always generating one word or one token, and then we append this token to the input, and we put the input again through the LLM and so forth. And if you have used a web application like ChatGPT, for example, if you type in a query and you pay close attention to the output, you might see there's one token or word appearing at a time when it generates the output. And that's because it's an iterative process. It's not generating the whole response all at once. It's doing it step by step. And so how does that work? Here is an overview. It's maybe very technical, but we will get through this, I promise you. So what you are seeing here is, again, the input, hello, I am. And for now, please ignore anything about below the dashed line. So the input might be hello, I am. And then similar to what we've done or learned in chapter 2, first we convert the tokens from a string representation into a token ID, into an integer representation. So we are converting text into token IDs, and then we put these token IDs into GPT, the GPT model we just coded in the previous section. And then, like we've seen, it outputs this tensor here, and it has 4 rows. And each of the rows corresponds to one of the input words here. And if you recall, a long time ago, but if you recall from chapter 2, the way we set up our data loader was that the targets are the inputs shifted by 1 position. So the way we are going to train the LLM is that for each token, it will associate the next token because of the +1 shifting that we implemented in the targets. So what that ultimately means is at each position, this vector will contain information about the next position, about the +1 position. And so that means that the last vector, which corresponds to the last vector in the input, will contain information about the next word we want to generate. So the last row contains the information we need for the next word. But we need to now convert this vector back into the word that we want to generate. How does that work? One thing I wanted to mention is this last row, in general, these last rows here, they are also called logits. It's not a LLM term, it's a general deep learning term. I don't want to go into too much detail why they are called logits. That would go into a statistics lecture here. But in general, it's convention to call the output of the last linear layer. So the output of the last linear layer in a neural network is usually called the logits, so the values that come out of this linear layer here. So we call them logits. And so here we are looking at the logits of the last token. So we are just, copy pasting. If you pay attention, these are the same values. We're just copy and pasting here in this figure the last row, which we call logits, and then we apply the softmax function to normalize them. So they range from -infinity to infinity. So it could be very negative small values to very large values. And we convert them into probabilities, which are all strictly positive and sum up to 1. And by the way, this is an optional step. This is not necessary. You can actually skip this step because the smallest value always corresponds to the smallest probability, and the largest value always corresponds to the largest probability. So there is no need for the softmax, but it makes it a bit easier to interpret. And so what we're looking at is the normalized logits as probabilities, and we are interested in so maybe one step back, I should say again, this is 50,257 dimensional. So we have 50,257 values here, and each value corresponds to a token ID in the vocabulary. And now our goal is to train the network such that the correct next token that we want to generate has the highest probability. We are not training anything here. This will be done in the next chapter. But then let's assume we have a well-trained GPT model. It will associate the token we want to generate with the highest probability. So let's just assume this is a trained model, and it will have the highest probability in position 257. So this is the first position, position 0. This is the last position, position 50,257. And everything else is dotted out, so otherwise it won't fit. And this model happens to put the largest probability score here into this position, 257. And if we take our tokenizer from chapter 2 and we use tokenizer.decode, put in the token ID 257, it will generate the next token A. So this is the desired token we want to generate. Now, how does this actually, or maybe one more thing here is, we then take this generated token and append it to the input for the next round. So this is only showing you one round. And like I mentioned before, we do this in an iterative fashion as long as we want to generate more text. So every time we generate the next token, it's added to the input. And then we put this whole input again through this pipeline and so forth. But yeah, to make it maybe more clear, how does that actually work out in code? So let me go to the notebook and let me code this. So we can define a function, call it generate, let's say text simple. Why simple? Because we will be implementing more sophisticated versions of that in later chapters that contain some additional sampling procedures. But the simplest version, which is the one I showed you in the figure, works as follows. So we have the model that we pass to our function. We have the text, let's call them IDX, the index tokens. And then we pass the number of max new tokens we want to generate. We have to define a number, otherwise it will be infinitely generating more tokens. And then also the supported context size that the LLM supports. And then we have a for loop. So the for loop is for how many tokens we want to generate. And then we keep generating. And so here the goal at the end, so let's dot this out for the moment, and then we will return the modified index. So here we pass in the index, then here we keep appending to the index, and then we return it. So that is similar to what you're seeing here. In the beginning, in the first round, we have this input, and then we generate the next word A, and we add it to the input and so forth in an iterative fashion. Maybe this is a bit abstract. So what is index? So index correspond to the token IDs or token index positions, because the token ID corresponds to the index position in this tensor. So index position means 0, 1, 2, 3, 4, 5, 6, 7, up to 50,257. And that's the same as the token ID. So the token ID corresponds to the index position. If I say token ID or index here, in this case, means the same thing, because we're talking about the index position of this probability tensor. Okay, so just to have something to work with, we have this start context, just the first text we start with. We encode this with our tokenizer into token IDs. So let me just show it here. So these are our token IDs, and we can also call them indexes. And then we have, because our model only works with PyTorch tensors, we have to convert this list into a PyTorch tensor. So I can maybe just show it to you. So this is our PyTorch tensor, and I added the batch dimension here. So with this unsqueeze, I just added an additional dimension. So you can see this is now a 1x4 dimensional one. So because our model expects batches. So we only have a batch size of 1, but it's just for compatibility reasons. And then we can use that model later for training. Okay, now let's fill in the interesting part here. So we are going to code now our token generation. So first we're going to truncate. So what we're doing here is we are truncating it up to a size that the model supports. In our case, that if we have something like this, that's not an issue. It's just 4 tokens, and our model supports, what have we defined? Up to 1024 tokens. But let's say we copy and paste a large document, 50,000 tokens, so that the model doesn't crash. We just truncate it and pass only the first 1024 tokens. It's just like a sanity check. And then let me double check if I have 1, 2, 3, 4. Oops. 1, 2, 3, 4. That I just have the right spacing because it looked a bit off. It's just a Python convention. And then we compute the logits of the model, of the inputs. So this is corresponding to this one here. In PyTorch, though, one more thing I should add is the no grad context. So in PyTorch, by default, it is always building this computation graph of the model in the background that is used for the backpropagation algorithm, the training algorithm. And if we don't train the model, this is very inefficient. So here I'm suppressing the generation of this gradient computation, the computation graph, because we are not training here. We're just using the model. So it's just a good practice to save memory, so it's less compute intensive. And then what we are doing is we are grabbing the the last row. So here what I'm doing is I'm just getting the last row of the logits. Let me see here. This is what we're doing. We're extracting the last row. Okay, let's just do it like this. Why not? Next, what we are going to do is now we are computing the probabilities. So we use torch.softmax, similar to what we have done with the multi-head attention. Yeah, so we'll do that for the last dimension. And then we look up. So here maybe one more thing to explain. The argmax, we are using the argmax function in PyTorch. So argmax is let me just move that down here. The argmax function we are going to use next is a function in PyTorch that looks up the index position. So let me make an arbitrary example tensor. Let's do something like this. And so what argmax is doing, it's finding the index position with the highest value. Here, the highest value is the first value, so it should return a 0. Now, if I put this 14, or let me just put a larger one here, it should return 0, 1, 2, 3, 4. 4. So it is returning the index position of the highest value in the probus here. That's what we're doing. And let's call that the next index of what we want to generate. So here we are going over the last dimension because the first dimension is the batch dimension. So we don't want to get the largest, we don't want to mix up different batches. We want to have this for each. So here we are only looking at one batch, but we have maybe 2 rows if we have a batch size of 2. So we don't want to mix between batches. We want to keep them independent. So we are looking at the last dimension. And let's also keep them true so that the dimension matches the one that we have as the input, and then we can nicely, I hope, concatenate. Let's do index, next, and the dimensions is always something you have to keep in mind to make sure everything stays the same. And if I didn't make a mistake here, this should be adding the next generated token, which you see here, back to the input here. Basically, we're not converting back to text here. That is what we will do later with the tokenizer. We are here operating in this token ID dimension. Okay, so let's hope I didn't make a mistake, and let's try this out in practice. So for that, we are going to use this text, and then we will generate the output. We'll use our generate text simple. And let me just copy and paste here what we have. It's maybe easier this way. And then we assign the model here. The index is our encoded tensor. Max new tokens, how many do we want? You can experiment with this. Let's do 6. And the context size, yeah, let's just reuse this here. This should be context length. And hopefully this works if I haven't made a mistake. I did, of course. Oh, I think I forgot a colon, of course. So this would not work. Yeah, so I need a colon here. Keep them without the underscore. There we go. Now we have something. And let's take a look at how that looks like. So we have now token IDs. Now the last thing, of course, is to use our decode method to convert token IDs back into words. You can see this does not work. The reason is this is a tensor and our tokenizer works with Python lists. So we have to convert this back into Python lists. So first we can do maybe a squeeze to get rid of one dimension. So this got rid of one of the dimensions, and then we can maybe do a to list. I always forget if we need an underscore or not. Let's just see. Yeah, this worked. So we have a list now, and we can see what happens here. So we can see it generated something, but this does not look like what we want to generate at all. You can see this, of course, is our input context. This looks correct, but this, for example, does not look like at all what we have seen here. It doesn't say, hello, I'm a model ready to help. It is more like gibberish. And the reason is we have initialized our model with random weights and we have not trained the model yet. So the model training will be actually the topic of chapter 5. And once we have completed chapter 5, hopefully this will actually generate useful text. But yeah, again, we have this generate text method and we can actually reuse that after the training to see that this actually will help us generate coherent text. But yeah, stay tuned for the next chapter on training the model.
Get this book at Manning.com.